Okay, here we go. So, my name is Chris. I'm with DE-CIX R&D department and also with the INET research group at Technical University of Berlin. And I'd like to talk about ENDEAVOUR Towards SDN-enabled IXPs. This is joint work with Sascha and Florian. So, to motivate this talk a little bit, we all know that IXPs are part of the internet ecosystem, and we all have a mental model in our minds if we're talking about IXPs. So let me quickly recap what we have here. Like the picture on the right-hand side shows a very simplified version of an IXP. We have the layer 2 switching fabric, which in the easiest or in the simplest case is just a switch, and in a more complex case it can be multiple switches and a huge layer 2 broadcast domain. So we see two ASes, ASA and ASB, interconnect to the IXP, to the switching fabric. ASA maintains a connection over one port, and ASB has 2 ports at this IXP. If they want to exchange traffic, they just set up a BGP session, and then they get the traffic from A to B and B to A. This is like the simple case of bilateral peering. Nowadays, a lot of the IXPs offers also the route server as a service to the customers to make the interconnection part a bit easier. So both ASes, or in an ideal case for the IXP, everyone maintains a session to the route server. The route server gets the prefixes, does a best path selection, and redistributes it to all members. So in this setup, they can do multilateral peering. So, and to wrap this up, IXPs also offer, maybe besides the route server, other value-added services, such as DDoS mitigation, which could be blackholing, or other services like filtering at the route servers. It really depends on the IXP. So, but given this setup, IXPs also face challenges. So, like most of you in your network, the traffic is growing. We need to do something to keep up with the demand for growing traffic rates, and we want to maintain quality. And this also holds true for IXPs. So we have a steady growth of traffic volumes at the IXP. And in the case of DE-CIX, we got the issue, a simple switch doesn't do the trick. We need multiple boxes, and usually we need to have the top of the shelf boxes. This is disproportionately high capex, so it's quite expensive for us. So we need to think if we can find new ways to interconnect customers, or to build an architecture, to come up with an architecture of interconnection of our platform, which reduces the costs. So at the same time, the default protocol, or the internet protocol, is BGP, which is quite arcane and has an old interconnection model in mind. So it's quite static, set up for long time frames, each month or years, and not a lot of things are changing. So it's not really dynamic what we have there. And also it's quite myopic, so it has a limited topology visibility. We also have a control plane and reachability-centric setup, which does not account for other values or other information. Sometimes people get around this by adding new features to BGP, extend the protocol, or using communities to signal additional information towards customers, IXPs, or whatsoever. And also in this setup, it is quite hard to come up with new services or value-added services, since we always have to deal with the stuff which is there, like the BGP and the static sort of topology setup. So now, while we identified our challenges and like see what are the limitations of IXPs as of today, we at DE-CIX started an ENDEAVOUR. It's a research project funded by the European Commission. It runs for 3 years, and the ultimate goal is to bring SDN to interdomain settings. And we believe that IXPs are sort of an ideal place to start off with this, since they are sort of static and a lot of networks interconnect at just one single point, and thus it is ideal to begin to introduce SDN there. This project is not just a DE-CIX effort. Actually, it's with a set of 5 other partners: the Queen Mary University of London, University of Cambridge, LAAS CNRS, IBM Research, and Université Catholique Leuven. Oh, sorry, not good with French. And everything we produce, we have reports, and we continuously have to report to the European Commission, and all these reports with our results are publicly available. Also, the prototype we built is on GitHub, so if you're interested, you can have a look at our results, and we all will continue to keep this open access and open source. So the keyword here is SDN. Sometimes, if I was at such conferences, like 2 or 3 years ago, people presented SDN as like the holy grail, the silver bullet SDN. It will solve all our issues, and it will be a new ideal world for all of us. Well, that's probably not quite true, and we see that the hype goes down a bit by now. But what I was always missing is actually that no one really convinced me with use cases, because I want to see what can SDN do for me. And if this convinces me, I'm happy to use SDN, as I'm happy to use any technology which helps me to improve my service or my exchange. So that said, SDN is not the silver bullet, and I'm happy to not give a clear definition of SDN here, because for this presentation we just like to talk about the high-level view here. So what we did first in this project is to come up with use cases which are compelling for our customers. So our incomplete list of use cases is here. Like, some are beneficial for members, some for operators, and some use cases we grouped such as novel services. So here we try to convince people like what could be the benefit of deploying SDN at an exchange point. So if we focus at the member use cases, there is such a thing as port load balancing. So probably the big players in the market don't really have trouble to load balance their traffic across 2 ports and set the shares as they wish to, but we also see that smaller customers have trouble with it. I'm gonna give some figures on this later on. Also, Blackholing as a DDoS mitigation service it can be improved through SDN to be more flexible and way more fine-grained than Blackholing of today. Also, a use case is member-driven monitoring. Sometimes members just want to get a very detailed view of what's going on at the IXP, but we just don't want to constantly monitor everything and every traffic at the IXP. So in this use case, a member can request a monitoring, and we can set up the monitoring for them and deliver like a stream of flow information towards the customer. So there are also potential benefits for operators. For instance, controlling broadcast traffic, since in an ideal SDN world you have a centralized controller which is aware of all participants at an IXP, so you don't really need ARP or neighbor rediscovery. Also, regular broadcast traffic can be steered in a way more intelligent manner. What we also have is layer 2 label switching, because as soon as you have like a very complex layer 2 fabric comprising several switches, you need to have some routing logic in it. And of course, you can have use MPLS and on top of it emulate a layer 2 broadcasting domain again. But it would be way easier to just introduce layer 2 label switching. There are also novel services. So for instance, there are port-based congestion reporting. So sometimes some members at an IXP have congestions, or their port is saturated by 100 plus or more than 100%, And it would be neat to have an automated fashion to signal this to other members, so that they are aware and probably either switch to another exchange or use upstream or whatsoever. Also, we can anticipate an IXP as a marketplace. So we could imagine, like, for small networks, they could just go there and not just do peering, but they could also buy transport services, for instance. And the point being is not that it is impossible as of today, but what we envision is to have it really in an automated fashion, so that it does not require a sort of BGP or negotiation by email, but rather have an automated setup. And last, we have the service chaining. So we envision that customers with a special service on traffic monitoring or classification services could also go to an IXP, and this traffic could be rerouted through their service boxes, middle boxes, and then take the normal flow back. So this is just, as I said, an incomplete list of some of the use cases, and during this talk I'd like to introduce some of those in more detail, because I understand that this is like a very high-level picture here now with missing a lot of details. If you really want to have the full details, there's a paper we published in autumn last year, which appeared in the IEEE Communications magazine, and the title is Interdomain Networking Innovation on Steroids, Empowering IXPs with SDN Capabilities. And we give a lot of details which I cannot give here because of time constraints in this paper. So let's first focus on an SDX architecture, software-defined exchange architecture. Earlier we saw traditional IXP and saw the interconnection there, and actually we have more or less in the core the same picture here. So we have two customers and we have a switching fabric. However, this time there's also a centralized, logically centralized controller which integrates the route server or a monitoring platform. So this controller is able to do like the full control, steer the traffic or the frames in this case across the IXP, and always has like a full view of the states at the IXP. So you could do things such as steer different flows differently and differentiate different kinds of traffic or customers or whatever you want. So you have a central controller instance. And this central controller instance, again, can be programmed by applications. Such an application could be advanced Blackholing, traffic engineering, or congestion reporting. So you have this on top of the controller, and it could be used, like each member could use different of such programs. And they are then translated by the SDX controller into SDN configuration, or actually programmed into the switches here. So now I'm gonna talk a bit about the use cases we have. So there is the SDX use case, load balancing. So that's what I mentioned a bit earlier. Here on the plot we see on the x-axis all IXP members with at least 2 ports, and on the y-axis we see the share of traffic per port. And as you can see, like 1/3 probably uses a redundant setup, so they just have all their traffic on one port, which totally makes sense. But for some others, they use it in a very unequal way. So the share for one port is maybe about 70%, and the other port just 30%. For some networks, it totally makes sense to do so. But when we talk to customers, actually, some of them don't really know why this happens, and they don't really care too much. However, this could be optimized by defining a share, like across an API at the IXP or web interface, and just a customer or a member can just set up the share they want to have, like if you have 2 ports, probably 50-50, and the SDN controller can just do the traffic engineering here. This would be, we implemented it in our prototype through simple rules, and we just looked at the last byte of the source IP address or destination IP address, and then the last bit of the last byte makes the decision is the tiebreaker for a 50-50 decision, like where the traffic actually goes if you have 2 ports. So, but this is just a very simple example. We could also think about like way more sophisticated load balancing stuff, such as separation by application, just looking at the transport layer port and say, okay, traffic towards this application has to use this port, and the other application this port. This is just basically the proof of concept that we can do it, and we envision that customers will use this, or would use this tool for many things we cannot envision right now. So here's just an example where we visualized our evaluation test case. So we just started 4 different traffic flows, and we see, as we can see in the upper plot and in the lower plot, we can see like over time it converges to a equal share. Like we have 4 ports here, and it's just distributed across each port with an equal amount of traffic. So another example is always blackholing, and I know that security is a huge concern for a lot of operators, and a lot of people use blackholing at the IXP, and what they all report, it is quite limited in its capabilities, since it's all or nothing approach sometimes. So black hole, the example is it's announced with a specific next hop IP address, and black hole all the traffic for a certain IP from one or all peers. So in an SDX future, we would see it differently, because you can actually leverage like any field of the header. So you could go for the port, transport layer port, or actually like port at the IXP, just to have a good port and a bad port, and just filter at one of it, or as you wish, basically. So source IP filtering and whatnot. We could also do rate limiting, allowing a certain IP address to just have consume a certain bandwidth. So we're really flexible here. And our current work is that participants are able in our prototype, we implemented the way that it is by now possible to filter on MAC addresses, on destination IP addresses, and on the destination port. For instance, when we crunched some numbers and looked at some DDoS attacks and some DDoS traffic at an IXP, we saw that it's fairly easy to get rid of most of the attacks. For instance, just getting rid of UDP traffic helps a lot, or just to filter or discard traffic to a certain transport layer port. And also we can dynamically update the black hole policies as we wish on a sub-second time window. So if something changes, it is very easy and it's very dynamic and responsive, so that we can change the flows very fast as well. What we also can do now is visualize and really display the drop traffic, because this is at most IXPs an issue for now. As soon as you switch on blackholing, you have no clue how much and what kind of traffic is dropped actually. And in our SDN prototype, we're still able to display the traffic that is dropped, and also we could do some further analysis, such as what ports or to which ports should the traffic actually go, and so on, and from which IPs is it coming, and stuff like that. So here again a visualization of our prototype. It's an example. Like in the top plot, we actually see the traffic that goes into the blackholing, and on the lower part you see the traffic that actually still goes through the IXP. And we see that the spike on the top plot is just like the inverse, so you could swap it down and it would just fit in there. So this is just an evaluation use case, but we just really have this working on software in our prototype now. So another example is port-based congestion reporting. So these numbers were quite surprising for me, because usually you would just think that a port can be saturated by 100%, right? This is true for the ingress port, for the egress port, but actually ingress, the IXP gets from several sites traffic, and that can of course be more than 100% of the customer capacity. So it all goes in the IXP and actually gets lost when it directly goes to the customer. So that's why we see a long tail in this plot of customers that exceed their port utilization even by 100%. And we all know that 100%, I mean even 90 or 95 is probably critical already. And so other members would probably like to know which customers are there that overutilize their port and have some sort of direct signaling mechanism to help them to just get rid of their traffic elsewhere. So another thing that I just mentioned in the beginning is we would like to see CapEx reduction. However, for now, it's not that easy, because if we look into the market and look at SDN switches, they are not that much cheaper actually. So, and additionally, you have to implement everything from scratch, which is sort of risky to develop such code base. I mean, the vendors, hardware vendors, have done a good job over the past decades, and they implemented the protocols, and this stuff is basically quite solid. But here, the idea of Noviflow was to have a scale-out router, which comprises of some OpenFlow hardware in a spine leaf architecture, and also just a regular switch. And on top of it, the controller, so that at the end of the day, you sort of rebuild with smaller, cheaper parts such a huge box. But what we see from now, we are a little bit disappointed, because price-wise it doesn't scale. If you buy like top-of-the-shelf SDN switches for now in terms of bandwidth, it's like not really cheaper than buying commodity hardware. So this is limitations of SDN-capable hardware, and we're looking for SDN hardware with a number of available ports. So we really need a higher port density, and a lot of SDN switches just comes with a single table capability, and since we implemented all the use cases I mentioned earlier, and for most of the use cases we just need a single or dedicated table, so a single table setup would not work for us, and it's really hard to scale. Also, the number of TCAM entries is quite limited, and for a really large exchange, it could work somehow if you do some magic on the way to really reduce the number of flow rules. But in a more dynamic environment, in a more dynamic intra-domain routing environment, this is probably by far not enough. And one lesson we also learned is don't trust the barrier replies. So if you install a certain set of rules, the switch responds and says, hey, your rules are installed, but the reply is sort of fake, because testing has shown that actually it's not implemented in the hardware and the traffic does not flow as it should for those moments. So there's an inconsistent state at this point. So what are the future SDX challenges we are facing? So it's a bit what I mentioned earlier. We need to build reliable software, right? So we sort of have to start implementing everything from scratch. Each protocol, it starts like with really standard stuff you just configure on usual hardware. We need to implement it from scratch. And I mean, we are quite large IXP at DE-CIX, but we by far don't have the manpower to really implement such a huge protocol stack with a satisfying requirements on resilience and reliability. Yeah, and also, as I mentioned earlier, the SDN-capable hardware at scale is not there yet. So, we keep looking. And for me, actually, something ideal would be like a combination of both worlds. So having real huge boxes with also integrated SDN features to be able to offer some of our services and also use some of the protocols there. And another SDX challenge is the testing. So we would need extensive testing of the prototype before we ever could think about the next step to put it in operation at some point. We're also right now looking into just partial SDN architectures where some edge nodes are SDN boxes and the core boxes remain commodity hardware at this point. So I hope I could give you some insights in our progress and how the SDN world at the IXP looks. And I see that it is quite distant future. We're talking probably several years until such a SDN-powered IXP at scale exists, if it will ever exist. But we also learned that actually there are use cases, so there are needs by members, and there are things we would like to implement. And it's hard with the hardware as of today. So, thank you. And I'm happy to take questions now.
Testing. Oh, yes, we are on now. Good morning, Matt Petak from Yahoo. So one of the interesting challenges with the typical hardware that people are looking at for SDN infrastructures is in order to meet that happy, hey, it's cheap, it actually makes your data center more efficient price point, they have tiny buffer memory in them. And
yeah.
At the exchange point where you have unknown latencies, different size pipes coming and going, it's kind of the worst case scenario for trying to use a small buffer device as the heart of an IXP. Is this something where you're talking to hardware manufacturers about doing SDN-capable, small, stackable rack unit devices, but with big enough buffer memory to actually work in an IXP-type environment like this?
Yeah, exactly. So we had such discussions, but actually my feeling is that the SDN or like the startup pure SDN companies, they got so many requests from different sides. The data center people want that, the IXPs want that, and it's hard for them to really find a solution that works for most of them. And beside the buffer size issue, it's really the density is an issue. If I want to buy an SDN switch and like the top of the shelf vendor offers me 400 G ports, then, well, I can't really work with that.
So this is looking more at the software and hoping the hardware comes to meet you at some point. Gotcha.
Indeed.
Okay. Thank you.
Okay, thank you.